Hello and welcome to Lecture 12. In this short lecture, we're going to talk about generators and motors. I say this is a short lecture, and it is because it really doesn't introduce any new fundamental ideas, but instead is an application of ideas we've seen before, like the magnetic force on a current and Faraday and Lenz's laws. Let's take a look at our objectives. We want to learn that a generator is a device that converts mechanical work into electrical potential energy via a coil of wire rotating in a uniform magnetic field. Okay, so turning mechanical work into electrical energy. In other words, inducing a current due to a changing magnetic flux. That right there is Faraday's law. Okay, but in practice. Okay, we also want to understand the key dynamics of a generator and the mathematical relationship between angular velocity and the EMF. We want to relate the ideas of a generator to a motor, compare the two, and say that a device that converts electrical energy into mechanical work, and see how this relationship leads to the concept of back EMF. Okay? All right. So let's talk about our first key term, a generator. Well, it is a device that converts mechanical work into electricity. It involves the rotation of a coil of wire through a uniform magnetic field. Okay, so this would be the input work right here. So you could turn it by hand or have maybe falling water or rising steam turn this input, okay? And as that happens, this coil, right, which is just a conducting coil, right? There's no current running in it until it starts to turn. But once this wire starts to turn, this wire that if is formed into a coil, a current is induced, and that current then flows through the resistor, then that can generate, say, power like in a light bulb. Okay, here's a little picture of what's going on. So if we consider the length of the coil and the cross length of it, right? So or the width of it as A and L, and then L times A would be the total enclosed area of the coil. Then we can think about that as the cross-sectional area. We can think of a normal vector that is normal to that area, and that'll come up when we talk about what's happening in terms of the actual amount of magnetic flux, and review magnetic flux in lecture 11 as the real basis of these ideas. The magnetic field here is labeled. The wire is being rotated at an angular velocity of omega. Okay, we assume this will be a constant angular velocity for our purposes. So we're going to assume uniform circular motion. And we can see here the induction of a current. Okay, and that current is going to get induced in this direction. Okay, it's going to get induced in the opposite direction of the motion of the electrons. Okay, so we can see that the current is going to move in the clockwise direction because the electrons are going to experience a force in the counterclockwise direction. And that's just because, of course, electrons move in the opposite direction of the conventional direction of current. And we know that the electrons are going to move in this direction from the full right-hand rule by just saying, okay, well, at this point in time, when the magnetic field points to the right and the electron sitting in that wire has a momentary or instantaneous velocity pointing straight down, by the right-hand rule, we see then that there must be a force that points back into the page, and indeed, that is the force on the electrons that actually induces the current. Okay? We can also conceptualize the induced current due to Lenz's law and say that the induced current must oppose the change in flux. Okay? At this point, what is the flux? Well, at this exact moment in time, the flux is zero, isn't it? Because none of the magnetic field is actually crossing through the enclosed area. But of course, a moment later, as the coil rotates, the magnetic flux will start increasing until a maximum magnetic flux, which will be a half rotation later. Because at that point, the loop will be vertical like this, and the magnetic field will be completely passing through it, and flux will be maximum. So do notice then that the actual induction of the current and the flux are not in phase, okay? All right, and the EMF generated by a generator is cyclical in nature because it's uniform circular motion coming in, all right, and it's due to that rotation. And so the output is indeed sinusoidal current. It is the natural creation of what's called alternating current, which I'll discuss in a later lecture. Okay, so that's the basic concept of a generator, turning mechanical work into electrical energy by rotating a coil in a constant magnetic field. But what about a motor? Okay, Well, a type of motor is an electric motor is a device that turns electrical energy into mechanical work. Okay? It's just a generator in reverse. Okay. Well, how does that work? Well, just imagine that instead of having input of mechanical energy, instead you ran a current through this coil. Well, if you were to run a current, that current is going to experience a force in the magnetic field, and thus it will start to turn. So in that case, you can just get mechanical work out for electrical energy in. And indeed, we can consider a motor and the result of the motor with this graph here. And this calls to attention that out of phase nature of the flux and the actual induced EMF. So consider these diagrams down below. This is an example of a current carrying loop that is being turned through a magnetic field. And so we see here that we have the motion of the electrons that are parallel to the field. Well, in this case, there is a maximum flux, and here's the flux, which is just the magnetic field or the cross-sectional area and the magnetic field. Okay, so this represents the flux. Okay, and this is the rate of flux per time. All right, and so we see then that the flux is maximum here, as denoted by the fact that this function is at a maximum, but the induced EMF is zero. The induced EMF is zero because the velocity is parallel to the magnetic field, so it experiences no force. A half turn later, the velocity is exactly perpendicular to the magnetic field, which now means there's no flux, but maximum induced EMF. So that's what we see, is that they are out of phase by pi over 2 radians, or a quarter of a full rotation. So they're always 1/4 rotation out of phase, the magnetic flux and the induced EMF. Okay, and that is true for both motors and generators. The principle holds for both. Okay, so what about back EMF? Well, a current is provided in order to create a torque. That's what I said. You put the electrical energy in and you get the mechanical work out. But once the coil starts to turn, it becomes a generator. There's no way for it not to follow the same exact principle that we discussed above. Because even though you're running a current through the coil, and that current is thus experiencing a force that starts to generate a torque, right? A force multiplied by a moment arm that twists the current carrying coil. But once it's moving, now those charges have a velocity, right? And as they experience the velocity through the magnetic field, they're going to start getting moved. And they're going to move in the exact opposite direction of the original current. So the induced current in a motor always goes exactly opposite of the original current that started the coil turning. And that's simply due to Lenz's law, because Lenz's law says the induced current opposes the change in magnetic flux. Well, the magnetic flux was changed due to the input current. Thus, the induced current opposes the original current and opposes the induced or the original current. Okay, and so we call it the back EMF. The induced current is called the back EMF. Okay, so let's read this out. However, once the coil starts to turn, it becomes a generator and provides an opposing current with an associated back EMF. Okay, so every motor is a generator. You don't want it to be. Now, no one wants a motor to be a generator, but it is inevitable in the design of an electrical motor. And therefore, you have a design of a motor means you have to put in extra current to account for the lost current due to the back EMF. Okay, and we'll see that in practice in a simple equation. Okay, which is a great segue to our equations. Okay, so let's take a look at our key equations. All right, so first of all, we'll talk about the generated EMF, right, for a generator. Okay, which obviously both motors and generators are generators, so this applies to both. Okay, and we have here the expression for 2, okay, times the magnetic field times the length of the wire times the perpendicular component of the velocity. Why 2? Well, because there are 2 lengths of wire that are actually going to be generating current. They're the 2 lengths that run in these directions, because the green lengths of wire, the ones I have highlighted green, will never generate a current. The forces on the free electrons, the excess electrons in this conductor, that the conducting metal of the wire, the forces that they're going to experience, that these electrons are going to experience, are only going to push them against the sides of the wire. They're never going to experience a force that's actually going to generate a current. Okay, they'll generate small eddy currents on the scale of the width of the wire, but never a net current in the sense of being clockwise or counterclockwise. So they're effectively useless for generating that current. So we're only going to consider the two lengths that that can generate a current. Okay, and then we're going to replace the perpendicular component with v sine theta. Okay, and sine theta is the angle between the velocity vector and the magnetic field vector. Okay, and then we're going to replace the v with omega times r, okay? Because v equals omega times r. This is a relationship between translational motion and rotational motion. Well, r here is the length or the distance from the axis to the point of rotation. Well, if we look up here, the axis runs right down the middle, the dotted line, so the distance out to where the free electrons that are generating the current are located is, yep, a over 2, half of the width. Okay, so that's where that a over 2 comes from. All right, and then we can then combine our L times A with the 2's that cancel. See how the 2's cancel out? So the 2's cancel out. And then L times A, well, that's just the enclosed area. That's big A, okay? And furthermore, we can replace the angle with omega t, which we're allowed to do because it's uniform circular motion. And in uniform circular motion, all right, circular motion, theta does equal omega t, okay? Because there's no angular acceleration, so we have a direct relationship, theta equals omega t, okay? So this is our final expression for the induced EMF for a generator that's rotating at a constant rate through a uniform magnetic field, okay? All right. And furthermore, all right, area enclosed by the loop, all right? And furthermore, when there's more than one loop, right, when it's not just a single rectangle, when it's more like a solenoid or a series of stacked coils, we can count the number of turns or the number of loops by just tacking on a value of n, which then increases the generated EMF by however many loops there are, all right? Okay, so it's a geometric increase. Just multiply by n. And finally, the concept of back EMF, okay? So this is the current through a motor, right? This is the input current into a motor because you put current into a motor in order to get mechanical work out, all right? But then that motor starts behaving like a generator, and when that happens, you get your back EMF, all right? So you see then that the current through the motor is less than it would be if there wasn't a back EMF, okay? So really, this isn't really the input current, this is the total current, because there's some input current, but then some of that's lost. So then you have to, and so that's accounted for with this negative term in the numerator. Okay, so this is the effective total current through the motor already accounting for the back EMF. All right. Okay, so let's take a look at question 1. I have a concept question in 3 parts, which I think will be a good demonstration of this idea of the phase angle between magnetic flux and the actual generation of current motion. Okay, so a generator generates maximum EMF at what angle between the electron's velocity vector, okay, and the magnetic field vector. All right, so when is the EMF the greatest? All right, well, we know from this equation that the maximum EMF is just NBA omega. All right, so that's essentially, this is the amplitude of the function. All right, this is EMF is a sinusoidal function with this being the amplitude. We saw that on the graph on the previous page. That was the amplitude of the sine curve. All right, so that's as big as it gets. It's the maximum induced EMF. So when does that happen? Well, that happens when sine theta equals 1. Well, what must theta be? Theta must be 90 degrees, right? Or pi over 2 in radians. All right, so 90 degrees must be the angle between the velocity vector of the electrons and the magnetic field for maximum induced EMF. Okay, and 90 degrees was actually the example in the diagram. That was the angle that I showed in the picture between the velocity vector and the magnetic field. Okay, all right, well, what angle will exist between the velocity vector of the electrons and the magnetic field when the EMF is half the maximum value? Would it be 45 degrees? No, because let's think about it. In this case, we want 1/2 the maximum, all right, which then we can write as 1/2 NBA omega. And then we're going to then cancel out the expressions because we know that Emax is just NBA omega, all right? So then we just have 1/2 equals sine theta, All right, then we're going to do an inverse sine function to solve for theta. And when we do that, we get 30 degrees. So maximum occurs at 30 degrees. But we should expect that, because if you think about sine functions, you know what sine of 30 degrees is? 1/2. So there you go. All right. And finally, what is the relative amount of magnetic flux through the loop of the generator when the EMF is 0? Well, induced EMF is 0 when theta equals sine inverse of 0, which is 0 degrees. So we see that the magnetic flux is maximum when the angle is 0 degrees, okay? So that happens, right, when there's no induced EMF. Then there's no induced EMF because this corresponds to a velocity vector of the electrons being parallel to the magnetic field. So it's not good for inducing EMF, but that does coincide with maximum flux, okay? All right, so enough about the theory. Let's do a few simple calculations because the problems that involve generators are not terribly complicated at this level of the class. Example 1. What is the minimum frequency with which a 300 turn flat coil of cross-sectional area 370 square centimeters can be rotated in a uniform 25 millitesla magnetic field if the maximum value of the induced EMF is equal to 8.6 volts? All right? So we know that maximum induced EMF occurs when theta equals 90 degrees. All right, and we know it's going to be equal to NBA omega, that's the amplitude. All right, so then I'm going to set the maximum value of induced EMF equal to NBA 2 pi f, okay? And then I'm going to solve for the frequency. And notice what I did. I replaced angular frequency with 2 pi f because omega, the angular frequency, equals 2 pi times the translational frequency. All right, omega is measured in radians per second, and frequency is measured in hertz. Okay, but now it's simply a matter of solving for that frequency. So we plug in all of our known values because we know the input, or we know the output of the induced EMF, 8.6 volts. We know that there's 300 turns. We know the strength of the magnetic field, and we know the enclosed area, which I've converted to square meters as is necessary. And there we go, 4.93 hertz. So not terribly fast. All right, so it needs to be rotating at about 5 times per second. All right, so 5 complete rotations per second in order to get this much induced EMF for this particular strength field and that size loop with that many turns. Okay, all right. Example 2. A motor has an internal resistance of 12 ohms. When running the motor, it has a back EMF of 29 volts and draws a current of 3.7 amps. What is the supply voltage in this case? All right, so it's simply a matter of setting up our equation for back EMF. All right, and then we know that we have an internal resistance plus the back EMF, right? So we have I times R plus the back EMF, all right? So our 3.7 amps times the 12 ohms plus the 29 volts of the back EMF means that our supply voltage is 73.4 volts, okay? Very good. And basically all I did here is just solve for E from our equation, just isolate E, all right? Which is our supply voltage. All right, final example. Example 3. I told you it was a short lecture. A 580 turn circular coil with an area of, well, 0.055 square meters is mounted on a rotating frame, which turns at a rate of 17 radians per second. Right, that's the angular frequency. In the presence of a 0.04 Tesla uniform magnetic field that is perpendicular to the axis of rotation. What is the instantaneous EMF in the coil at the moment that the normal to its plane is at 50 degree angle to the field, right? So here's the picture. There's the normal of the plane, all right? There's the angle we're looking at. There's the magnetic field, all right? So we're simply going to use our formula for induced EMF, all right? And we're then going to, well, realize that we have all of our values, okay? And indeed, this angle is the exact angle that we want. Now you might say, well, isn't this the angle between the velocity vector and the magnetic field? Well, but this angle also works here for being the angle between basically the induced EMF and the magnetic field. And we know that it works because if we think that once this angle becomes 0, then there is no induced EMF. Well, sine of 0 would be 0, and indeed that would exactly coincide with the normal vector being parallel to the magnetic field, okay? So the normal vector and the velocity vector of the electrons, they match up. And we can even consider an electron right here and consider its velocity vector And indeed, we see that it's parallel to the normal vector, so they both serve the same purpose. So that's really kind of the one trick to this problem. And there we go, 50 degrees. We plug in all our values, and we find that our induced EMF is 16.6 volts. Okay, well, that wraps it up. I hope this lecture has been interesting and informative. Thank you so much for watching.